Woohoo and welcome back. Today we're going to be studying the Richter scale, or at least looking at it, as a way to approach logarithmic scales. One of the ways we use logarithms is to describe things, quantities that have wide-ranging values. And in the book, we look at things like measure of sound, so decibels, or the measure of pH, like in chemistry and physics. And today we're going to be talking about earthquakes. And earthquakes are going to be measured by intensity on a seismograph. So if you imagine that's the machine that goes boopida 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 when there is a big earthquake. It actually draws out the earthquake, and we can measure the amplitude, how high those waves are. And so what we're going to do is we're going to take that measurement of any earthquake and compare it to a standard earthquake. Now, a standard earthquake, someone else named this, is 1 micron. So very, very little. Let's just go boop, like that, little tiny one. And we're going to compare it to an earthquake with an intensity of 25 centimeters. Now, if you're not used to measuring things in centimeters, if you're used to inches, then a nice approximation is to divide by 2.5. It's not exact, but it's close. So if I divide by 2.5, well, that's about 10 inches. And in fact, it's a little bit less than 10 inches. So if you can imagine, the amplitude of the waves are 10 inches. So this is a pretty big earthquake. This is rocking and rolling. And what we're going to do is we're going to take the intensity. So how big our earthquake is and compare it to S, which is the intensity of the standard earthquake at 10 to the negative 4 centimeters. And then we're going to take the logarithm of that. So let's go ahead and see if we can calculate it. So our magnitude is going to be the log, and this is common log base 10, of 25 over 10 to the negative 4. So that is quite a lot. Because why am I saying it's quite a lot? Well, remember, 10 to the negative 4 is really 10 to the 4th up top. Remember, if we move a negative exponent, because it's not happy, up to the numerator, we make it a positive exponent. And so that's 10 to the 4th, right? Which is 100 times 100, which is what, 10,000? So this is actually quite big, but we're going to bring this right back down to a scale that we can understand by taking the logarithm. So it's not going to change the order of things. Bigger things are going to have bigger logarithms. Smaller things will have smaller logarithms. But instead of having to work with the number, let me actually write this out. 25 times 10 to the 4th is 25 and then 4 zeros. So 250,000. Oh, that was exciting. What did I forgot? I got so excited about the 250,000. What? I forgot our logarithm. So that would be a very large number, and we'd be telling people, yes, it was a magnitude 250,000, but is so big, it's hard to keep in mind what's going on. So for this scale, let me move you over, Godzilla. Thank you so much, sweetheart. And then over here, we're going to take the logarithm of that. So we're going to take log of, and you could either do 25 times 10 to the 4th, or you could write out the 250 or 250,000. And we're going to end up with a log of that is 5.39794 and some other stuff, which is approximately a 5.40 if we round to 2 decimal places. So that's a 5.4 on the Richter scale. So that's what it means. If there's a 5.4, if someone says you've just had an earthquake of a 5.4, then that means that it made the seismograph move 25 centimeters. So that's what that means. And so it allows us to compare easily without having to write out 250,000. And then if as these numbers get bigger, the numbers would just get too big to keep them all easily in a comparable, easily understood fashion. So logarithmic scales allow us to simplify. And remember, what does a logarithm do? Remember, log is log base 10. So when we look at a logarithmic scale, we're asking how many tens are there multiplied together? And we've got the 4 tens here, and then we've got another 10 times a 2.5, right? Because 25 is 10 times just about times 2.5, exactly. So we've got about 5 tens and a little bit, and that's what it's telling us. How many tens are there? And so instead of keeping the whole number in mind, we're just keeping track of how many tens there are multiplied together. So, okay, what does that mean then moving forward? Well, in 1989, the Loma Prieta earthquake that shook San Francisco and Palo Alto, it knocked me right down on my face. It made me laugh quite a lot. Had a magnitude of 7.1 on the Richter scale. How many times more intense was the 1906 earthquake in San Francisco? So if it was an 8.3 versus a 7.1, how much more intense? Well, let's think about this. If this is a logarithmic scale and you're counting the tens, this is about, to go from 7.1 to 8.3 is about 1. So it means 10 times more. Let's see if that works out. So that's the rough estimate. Let's take a look. So I've written some of this out so you don't have to read my handwriting to understand it. So magnitude is the common log of intensity over the standard intensity. And this is measured by the amplitude of a seismograph reading taken 100 kilometers from the sorry about that. That should say from the earthquake, the epicenter of the earthquake, and S is the intensity of a standard earthquake, just like it was up above. So if M is the log of the intensity over the standard intensity. Now, stay with me, okay? Let's do this. Let's do this one step at a time. Don't panic. Don't look ahead. I know the red pen came jumping out. Can I help? No, you can't. Not right now. Okay, come here. We got our support lizard, Godzilla, our support carnivore. We can do this. Okay, so what did I do? I know everyone's brains are like, numbers. Take a deep breath. M is the magnitude. So I want to know the difference between the magnitude of the first earthquake minus the magnitude of the second earthquake. And then I just wrote out the formula, log base 10 of the intensity of the first earthquake over the standard minus log base 10 of the intensity of the second earthquake. So far, so good, right? This is just the definition. Okay, so over on the left side, I've left it the same. Yeah, left it the same. You see what I did there? Over on the right-hand side, I used the law of logarithms. Right? And that said log of A minus log of B is just log of A over B. Right? So I use the fact that when you subtract logarithms, you're really just dividing what's inside them. Okay, so that's there. And then what's the next thing I'm going to do? I did a lot in this step. So the first thing I did was I noticed I had the intensity compared to S and the intensity of the second one compared to S. I can cancel the S's. So over on the right, I just have intensity 1 over intensity 2. Then I raise each side well, there's a better way I could say it. What would be a better way to say it? I don't want to say I raise each side because I could say that. But really, I use the definition of logarithms to convert to exponential form. And what does that do for me? That allows me to just get the intensities together. And I've got the two magnitudes right here, which I do know. One magnitude was an 8.3, one was a 7.1. And I'm going to need some handy dandy paper because I want to write a little bit more here. So if I've got that happening, what else do I have? So then I have 10 to the 1.2 equals I1 compared to I2 divided by I2. What if I multiply by the intensity of the second earthquake on both sides? Then I get the intensity of the first earthquake is the intensity of the second earthquake times 10 to the 1.2, or I could rewrite it as the first earthquake, so 1906 intensity of the 1906 earthquake equals 10 to the 1.2 times I2 and this was the 1989 earthquake. And remember, intensity is that measurement of how far the seismograph moves during the earthquake, right? So how big those waves were. So then I can just take a look. I can say, what is 10 raised to the 1.2? So I can see that it's about 16 times the intensity. I was going to say as intense, but I'm not sure that we can get away with that in physics. So in other words, we were right. It was about 10 to the first, but it's 10 to the 1.2, which turns out to be 16 times as intense. So anyone who was around for the 1989 earthquake, that was pretty intense. It did. It knocked me down. It knocked a bunch of stuff down. It hurt a bunch of people. It was intense, but it wasn't as intense as the 1906 earthquake. The 1906 earthquake was 16 times as intense as that was, which was pretty impressive. So that's it. You guys are awesome. You made it through some kind of scary looking math, so I'm very impressed with you. Woohoo! And we have finished the section on logarithms. Yay! So go get some fresh air, or go get some sunshine, or go get some darkness, whatever it is that makes your heart happy. Know that you're amazing and brave, and I'm very proud of you. And I hope that you have a great day / night / whatever it is you're having. And woohoo, and math on.